All right, today we're starting with Chapter 2, Section 1, Inductive Reasoning and Conjectures. The last 3 to 4 minutes you should have been working on determining the next 3 things in each of these patterns. So probably the first thing that you would have needed to look at was what is happening in each of these. So in the first of our patterns, hopefully most of you were able to get this, going from 2 to 14, we were adding 12. To go from 14 to 26, we add 12. And so our next number that we're going to have would be that 26 plus 12, which gives us 38. If we add 12 again, we get 50. And if we add 12 one more time, we get 62. So the next 3 numbers in our pattern should be 38, 50, and 62. As we go through, we'll find that the patterns get a little bit more and more difficult as we go. In the second pattern here, we have the numbers 1, 4, 9, and 16. And these ones do follow actually 2 different patterns here. We can look at it as going from 1 to 4, we add 3. Going from 4 to 9, we add 5. Going from 9 to 16, we add 7. So if we look at that, it looks like it's a progression of the odd numbers. So we have 3, 5, 7. The next number that we must add is 9. If we add 9, we get 25. The next odd number in that progression would be 11. If we add 11 to 25, we get 36. And if we add 13, which is the next number, we get 49. So the next 3 numbers would be 25, 36, and 49. Now hopefully you recognize that the numbers here, 1, 4, 9, 16, 25, 36, and 49 also follow a different pattern, and that is that they are all square numbers. So we have 1 squared, we have 2 squared, we have 3 squared for 9, we have 4 squared for 16, 5 squared, 6 squared, and 7 squared. So kind of 2 different ways that we could have looked at that pattern. One is by adding consecutive odd numbers, and one is looking at it as a pattern of squares. For the third pattern here, we are doing something over and over again. The first thing that hopefully you would have noticed is that we're going from negative to positive, to negative, to positive, to negative. And since we're doing that, while we're actually decreasing the number itself, hopefully you recognize that we are dividing by a negative number, and that negative number is 2. We divide by negative 2 again, we get negative 4. Divide by negative 2, we get 2. If we divide by negative 2 again, we get negative 1. And if we divide by negative 2, we get 1/2. Dividing by negative 2 again, we get negative 1/4. And dividing by negative 2 one last time, we get a positive 1/8. My guess is that most of you were able to get at least 2 or 3 of those patterns, and which is good that we have that intuitive part already down. This last pattern from past years of teaching, my guess is that very few of you were able to come up with a pattern here. If you did, that's great. Like I said, just in the past, very few have. So what's happening? Going from 1 to 1, nothing's really happening. But if we take 1 and add 1, we get 2. So if we take 1 and 1, we take 1 and 1, we add those together, we get 2. If we take 1 and 2 and add them together, we get 3. If we add 2 and 3 together, we get 5. So each number, each consecutive number here, is the sum of the previous 2 numbers. So 5 is the sum of the previous 2 numbers, 2 and 3. 8 is the previous 2, 3, and 5. And so our next number that we have is the sum of 5 and 8, which gives us 13. Then we do 8 plus 13, which is 21, and 21 and 13, which is 34. And so on and so forth. We would just keep adding the previous two numbers together to get that. This is a special number or special sequence in math where we add the previous two numbers, and it is called a Fibonacci sequence. Adding the previous two numbers to get the new number is called a Fibonacci sequence, named after the mathematician Fibonacci. All right, so if you didn't have any of those, hopefully you did copy them down as we went. Continuing on our notes, today we're talking about inductive reasoning. This is reasoning that uses a number of specific examples to arrive at a conjecture. This is examples to arrive at a conjecture. A conjecture itself, we talked about this the other day in class. A conjecture is a concluding statement reached using inductive reasoning. In class the other day, we talked about it two other ways. We said a conjecture is kind of like a hypothesis in science, where we're taking kind of a researched guess at what might be true about what's going on. Here, it should be a little bit more solid than that, like it's actually going to be true. But conjectures can be false, but when we look at homework and stuff that says make a conjecture, you should be trying to make your conjecture true. And then a counterexample, this is just an example that we can use to show that a conjecture is false. So if we have a conjecture and we want to show that that conjecture is false, the only thing we need is one counterexample, one example that shows that the conjecture is not true. Give you 10 seconds here if you need to finish up writing any of these. All right, so we want to make a conjecture based on the pattern here. So there's a few different ways we could look at this. The main one is, just in case we don't know, what's in the diagram here are supposed to be like toothpicks. So we have toothpicks making up these square arrays. And for the first one here, the square we have is made up of 1, 2, 3, 4 toothpicks, right? So our first one is made up of 4 toothpicks. Our second one, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We have 12 toothpicks that make up this array, right? And then finally, in the last one, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. We have 24 toothpicks that it takes to make up our final box there. And so what we want to do is to try to come up with a conjecture about these statements. So in other words, we have 1, we have 2, we have our third pattern. A conjecture then would be what's our fourth pattern going to look like, and how does it relate to the pattern that we are already looking at. So I want you to take a minute and just think about that for a few seconds here. Okay, so we have, again, we have our patterns here, and we have 4, 12, and 24. What you might notice is that to get from 1 to 4, we would multiply by 4. We have 1 times 4 for our first pattern. For our second pattern, we have 2 times 6. And for the last pattern, we have 3 times 8. And so it would make sense that in our fourth pattern, we would have 4 times 10, where each pattern is increasing by 1. So we have 1, 2, 3, and 4. And the number we're going to multiply by the second part is increasing by 2 every time. So we have 4, 6, 8, and 10. So that's one way that we could talk about the conjecture of this pattern, right? The second thing that we can do here, and maybe this one you noticed more easily, is that we also could talk about this where we look at how many boxes there are. So in the first one, we have 1 box being made. In the second, we have 4. In the third, we have 9. So in our first set, we have 1. In our second, we have 4. In our third, we have 9. And that should be a pattern that we recognize already, because this is one of the patterns we looked at to start the day off. This is 1 squared, this is 2 squared, and this is 3 squared. So in our first pattern, if you square it, we get 1. That's how many boxes there are. In our second pattern, if you square it, we get 4. And there are 4 boxes. And in our last one, if you square it, we get 9. So there'd be 9 boxes. And if we had 4, right, if we looked at our fourth pattern, we would expect there to be 16 boxes because that's 4 squared. All right, the next thing that we're going to look at is making some conjectures about statements that are given. So the first conjecture that we want to look at here is the product of 2 consecutive integers is divisible by what? So what, if we have 2 consecutive integers that are being multiplied together, right? If we look at the product, we're talking about multiplying, right? So if we multiply 2 consecutive integers, what will it have to be divisible by? Well, let's take a look at what is 2 consecutive integers, right? So if we don't know what one of the integers is, then one of them we can always describe as n, right? And consecutive to n would be something like n plus 1, right? Consecutive integers then would be numbers like 1 and 2, or 7 and 8, right? It's just adding 1 anytime that we have it. So here, the product of 2 consecutive integers is divisible by what? Well, we have n times n plus 1. That gives us n squared plus n. And there's a much better way to describe this. So if we talk about it this way, n could be either positive or negative, or not positive or negative, it could be positive or negative, but it could be even or odd. If it's even, right, we would have an even number squared, which is even, plus another even, which gives you another even number, right? Or n could be odd, and we would have an odd squared, which is still an odd, plus another odd, which always gives you an even. So no matter what, this is going to come up with an even number. Like I said, there's definitely a better way that we could describe this, and that is by, instead of using n and n plus 1, we use 2n and multiply it by 2n plus 1. Now, this seems a little bit weird, but this gives us the option where we have to start with an even number because 2n has to be even, and then 2n plus 1 has to be an odd number. And then from this, we can see that when we take the product, we get 4n squared plus 2n, which has a factor of 2. So we have 2 times 2n squared plus 2. Any number that is multiplied by 2 is automatically an even, which means it's automatically divisible by 2. All right, the second one here, the sum of two negative numbers. Sum of two negative numbers. So if you take a negative number and you add another negative, right? Sum is add. You add a negative number. Let's take a look at our number line here, right? So say we have 0 and we're starting with some negative number and we're going to add another negative number. We're going further to the left, right? So what would it be possible to have if you take two negative numbers and add them together? It would be impossible to get to an even number. So if I were to make a conjecture here, my conjecture would be the sum of two negative numbers is negative. Right? The sum of two negative numbers must be negative. It cannot be positive. All right, the third one here, the product of two square numbers. So we could start by just making a guess. Again, product is multiplication. Square numbers are like 1, 4, 9, 16, 25, and so on, right? Now, maybe we don't know, right? So another way that we can look at this is by actually taking some square numbers and multiplying them together, right? So if we take a square number 1 times another square number 4, we get 4. Not really that interesting because 1's not a very interesting number a lot of times because it doesn't do what we want it to do here. So let's look at two other ones. Let's look at 4 times 16. 4 times 16 is 64. Okay, that's interesting a little bit, right? Well, what if we continue to look at some other ones, like 9 times 16, right? 9 times 16 would be about 114. No. 144. Do not have my calculator out. It is 144, right? And if we continue to look at other squares multiplied by square numbers, we would have something like 4 times 25, that's 100. Well, what do you notice about all of these numbers that we're getting? 4, 64, 144, and 100 are all actually perfect squares themselves, right? So if we're taking the product of two square numbers, it seems like we're getting perfect squares out as well. So if we were to make a conjecture here, the product of two square numbers is also a square number. Right? Is also a square number. You can go back and look at any of the squares that you want to, but you will find that this is true. You can look at why this is true, right? Part of this would be the properties of multiplication, right? If we look at this 4 times 25, it's 4 times 25 because 24 is not a square number, 25 is. I knew where I wanted to go with it. 4 times 25, that's the same as 2 times 2 for 4, times 5 times 5 for 25, right? That equals 100. While with multiplication, we can move things around, so we have 2 times 5 times 2 times 5, which still will be 100. And we have 2 times 5, which is 10, times 10, and that is 10 squared, a perfect square, right? And that would work with any of our other examples as well. All right, the last ones here, we're just trying to show that a conjecture is false. And to do that, all we need is one counterexample. One example that shows that the quotient of two numbers is always a whole number. And this actually should be pretty easy. The quotient of two numbers, we can pick any two numbers that we want, and we need to divide them, take the quotient of them, and show that it's not a whole number. Now, we can find plenty of examples that do work, right? We take 6 divided by 3, we get 2, which is a whole number. If we take 8 divided by 4, we get 2 again. If we take 25 and divide by 5, we get 5. And so there are plenty of examples where the quotient of two numbers is a whole number, but it doesn't matter if it works over and over again with 1,000 or an infinite number of solutions that work. If we can find one that doesn't, then this conjecture is false. And we find that there's actually a lot of places where this doesn't work, right? Pick any two numbers and divide them. 2 and 3. Well, 2 and 3 are numbers, and when you take the quotient of them, you do not get a whole number. You get 0.6, where that 0.6 is repeating, and by definition, whole numbers can't repeat. So this is not a whole number, so this would work. Now, that's not to say that everybody in the class has to have 2/3 as their answer, right? Somebody else could say, well, if you take 3 divided by 4, you also don't get a whole number. Or any two numbers, well, even -4 over 2, well, that's -2, and -2 is not a whole number. It's an integer, but it's not a whole number. Whole numbers have to be positive. And so even though -4 and 2 are both numbers, -4 divided by 2 is not a whole number. So there are a lot of different examples here. I would be surprised that if in a general assignment or something like that, we all came up with the same thing. Sometimes there is only one counterexample. A lot of times there's a lot. All right, the difference of the absolute values of two numbers is positive. So the difference of the absolute values of two numbers is positive. So what we're talking about is the absolute value of a number, A, and we're going to take the difference to take away the absolute value of B. And what this says is that whatever comes out has to be positive, right? Well, we know that absolute values themselves create positive values, right? But if we're taking the difference between two different absolute values, well, we can manipulate this a little bit differently, right? So what you could try to say is something like, well, anytime that B, in this case, is bigger than A, or but the absolute value of B, right, because it could actually be negative, is bigger than A, this is not true, right? However, because all we have to do is show a counterexample, what you want to do is come up with one specific example. So here, I might say something like, my counterexample is let A equal 1 and B equal 2. Then the result is negative. And the conjecture is false. Now again, this isn't to say that there's not a ton of other ways that we can do this. Not a ton of other ways we could do this, right? In fact, A could be 1 and B equal -2, and this would still be false, because we would still come up with a -1 as our answer. And so there's a lot of different ways. Anytime that B is bigger, the absolute value of B is bigger, this is going to be negative, not positive, and so this conjecture is false. Okay, if x squared equals 4, then x equals 2. I'm going to give you like 20 seconds here to think about this, because this one is a little bit difficult. We look at it and we think that it must be true, but I'm going to give you 20 seconds to think about why this is not true. In other words, you're looking for one case where x squared does equal 4, but x is not 2. So a case where x squared equals 4, but x is not 2. We're going to give you 10 seconds here. Okay, so my guess is that one or two of you might have gotten it, and most of you are still sitting there like thinking to yourself, well, if you take 2 squared, it is 4, so this must be true because the case we're giving is true, right? But what you want to do is you want to think about a way where we can have a different value for x other than 2 where x squared does still equal 4. And that does happen at one spot, right? It happens when x equals -2, right? Because -2, when we square it, is equal to -2 times -2. Negative times a negative is a positive, and we have +4. This was x squared, where we put in -2 for x, and we got 4. So x does not have to be 2 if we have x squared equals 4. This would be different than our last ones. This would be one where this is the only solution that works. Nothing else works. It has to be x equals -2. There's no other value that we have that would actually give you the correct solution here. All right. The square of the sum of two numbers is equal to the sum of the square of the two numbers. So the square of the sum is equal to the sum of the squares. Right? The wording here might feel a little bit weird because it's English and math doesn't always translate over right. So what you probably want to do first is to actually look at what this is saying. This is saying the square of the sums. So if you take the sum of two numbers, a plus b, and you square it, this is saying that the sum of the squares, a squared plus b squared, must be equal to that. And again, like our other ones, we can just kind of pick some values and see when and if they work or don't work. Here, it seems like it would probably be true, but this is that algebraic mistake that we often make because a plus b squared, this first part, is actually the same as a squared plus 2ab plus b squared, right? So it's not the same as a squared plus b squared, at least in almost any situation. And if we pick numbers like 1 for a and 2 for b, we have 1 plus 2 squared equals 1 squared plus 2 squared. Well, 1 plus 2 squared is 3 squared, and 1 squared is 1, and 2 squared is 4. And we would come up with 9 equals 5, which is not true, right? And so a equals 1 and b equals 2 is our counterexample because they are not equal to each other. All right, the square root of a number is always smaller than the original number. This is one of those common ones that you'll find. It seems like it should be true because if you take something and you square it, generally speaking, we get something bigger than the first. 2 squared is 4, 4 is bigger than 2. 5 squared is 25, 25 is bigger than 2, right? So what we want to look at here is some of those cases where things typically don't work out the way they were supposed to, right? Here, if you look at -2, so negatives are a good thing to look at as well, but if you take -2 and square it, you get 4. -2 is smaller than 4 as well, and so that one also doesn't work. And I've been going off about squares, and we're talking about square roots here. So square roots, the same concept, right? So when we take a square root, it's just the opposite of what I was talking about. So if we have the square root of 4, it's 2, and 2 is smaller than 4, right? If we take the square root of 9, it's 3, 3 is smaller than 9. But when doesn't this work? When does the square root of a number actually end up being something bigger, right? And so negatives actually don't work at all here because we can't take the square root of a negative. But on the other hand, we do have some numbers that do work, right? So one of those, and this is a number that you want to try to use often, that's the square root of 0. I'm not using the square root of 0, but 0 is often one of our counterexamples because 0 does some weird things. 1 is another example. 1 actually usually works out. So if you're trying things out For a counterexample, 0, 1, negative numbers are probably your first three choices, and then your fourth choice is to try fractions. So 0, the square root of 0 is 0. 0 is not smaller than 0, they're equal. So this is actually a counterexample. Again, I said 1 sometimes works. The square root of 1 is 1. 1 is not smaller than 1, and so the square root of 1 works as a counterexample. Like I said, negatives don't work anyway. We can't take the square root of a negative number, so we're not even going to look at those. But if we take the square root of a fraction, like 1/4, this is the same as the square root of 1 over the square root of 4, and we get 1/2. 1/2 is bigger than 1/4. So not only do we have ones that are equal, but we actually have some values that we have that are actually, the number is actually bigger when we take the square root of it, not just equal to. All right, lastly here, if n is a prime number, then n plus 1 is not prime. Right, so what you can look at here is pick a few prime numbers, right? So if we take 11, which is prime, and add 1 to it, we get 12, which is not prime. So that does fit this conjecture. If we take a different prime number, 13, and add 1 to it, we get 14. 14 is not prime. If we take 17, a prime number, and add 1 to it, we get 18. 18 is not prime because it's divisible by 2, right? And 19 plus 1 is 20. 20 is divisible by 2, so it's also not prime. 23 plus 1 is 24. 24 is even, so it's not prime. So generally what the problem that we're running into, if we go back, we could look at 7 or 5, right? Two smaller prime numbers. We have 8 and 6, the same problem. Equals 6, not plus 6, equals 6. If we look at 3, 3 plus 1 is 4. Again, we have an even. So what generally is our problem here is that most of our prime numbers are odd. In fact, there is only one example of where we have a prime number that's not odd, and that's actually going to be our counterexample here. Anywhere else, if you take an odd number and add 1, you have an even, and evens can't be prime except for 2. 2 is an even number and it is prime. It's even because it's only divisible by itself and 1. If you divide by 2, you get 1. So it's divisible by itself and 1, but it is a prime number then. So if you take 2 plus 1, you get 3. 3 is also prime, and so this statement is false because 2 plus 1 is 3 is a prime number. Your homework, which if there is time you can work on now, is page 95, numbers 14 to 46 even, and 55 and 56.